Today's presentation will be a brief review of the work what I have done during my studies. Also, as a main part, I will tell about the idea of using adjoint equations to increase the accuracy of the fictitious domain method. The object of my research is the numerical solution of the Navier-Stokes equation for the viscous incompressible fluid, two-dimensional Navier-Stokes equation. Why I consider this equation? Because this equation has a nonlinear part. There are some problems to be considered with this equation because this equation has a nonlinear part. Also, if consider this equation in curvilinear domain, it's very hard to solve this equation in numerical way. Also, there is no the boundary conditions for the pressure in this equation. Also, as known, it's Navier-Stokes equation is a problem which lasts for many centuries. Okay. In my research, I consider the Navier-Stokes equation exactly in the curvilinear domain. Navier-Stokes equation in a curvilinear domain can be solved in two ways. Its first way is using the finite element method by constructing the triangulated meshes. And the second method is using the finite differentiating method using the fictitious domain. I consider the two methods to compare them with each other. In the first direction, what I have done is I have written the code of the triangulation by using the advancing front method. Advancing front method is the one method of the constructing the triangulated meshes to solve the problem by using the method of the finite element method. How it works? What is the advancing front method? First of all, the curvilinear domain is discretized, so the polygon is constructed. So the polygon is constructed. Among all edges of the polygon, the minimum length polygon and minimum length edge is selected, and it is selected as a base of the isosceles triangle. And the isosceles triangle with a given ratio of the edge of the triangle to the base is constructed. And the area of this triangle is removed from the initial polygon, and the polygon is constructed again without this area. And in the second iteration, another edge with a minimum length is found and constructed new triangle. This operation lasts till the whole area of the polygon is filled by the triangle meshes. This is the main idea of the triangulation using advancing front method. Here, why I have drawn the two isosceles triangles, because of that. In the technical part of the coding, there will be such an issue that, for example, when you find the edge with a minimum value, you will find the middle of this edge, and with the given ratio, you will find the vertex of the isosceles triangle, and find the coordinates of isosceles triangle, coordinates of the vertex of the isosceles triangle. Sometimes this vertex may lie above the edge, above the middle of the edge. Sometimes it may lie below the middle of the edge. You need to select the right one, because that's why the concept of the vector traversal. The concept of vector traversal is introduced. For example, as you can see, vector traversal of this polygon's edge is the anti-clockwise, so it's a positive. So the vector traversal of the isosceles triangle should have to be also positive to this triangle lie in the inside of the polygon. If it's negative, then it's an error. No, this triangle is not taken as a mesh because this triangle lies outside of the polygon. how to find the sign of the vector traversal of the triangle. For this, the algebraic area of the triangle is calculated by the formula which is shown below. So after calculating the algebraic area of the triangle, if the algebraic area of the triangle is positive, then the vector traversal of the triangle is also positive. So it means that the triangle lies inside of the polygon. If it's negative, then this triangle doesn't lie inside of the polygon and is not taken as a mesh of the polygon. Okay, sometimes they may be needed to do some improvements. For example, let's consider such kind of rest of the polygon when you delete the meshes, remove the construct meshes, and you have the rest of the polygon like this, and construct the isosceles triangle, and the vertex of the triangle may lay very close to the vertex of the polygon, which is not appreciated in terms of the computing resources, right? And that's why it's suggested in this method to replace the vertex of the isosceles triangle by the vertex of the nearest vertex of the polygon. For this, the circle is constructed. Center of the circle is the vertex of the isosceles triangle. The radius of the circle is given as a ratio by user. For example, here I gave the ratio of the ratio such that the radius of the circle is a half of the length of the height of the isosceles triangle. So as you can see, in this case, in the triangle, there are two vertices, and the nearest one is chosen to replace the vertex of the isosceles triangle. So it's such kind of improvements. Then this construct triangle is also removed. Also the triangle, the ABC is also removed as a constructed mesh. This is some kind of improvement. Also, there may be cases of some errors. It may be appear that isosceles triangle may cross the edge of the polygon, which is error. This error have to be corrected. In this case, the vertex of the isosceles triangle is replaced by the vertex of the most appreciate vertex of polygon. This is the error correction part. This is also, to find these errors, there is some algorithm which is also considered in the code. Okay, this is the result of the code. Why I have written the code by myself? Because I couldn't find any codes which I can use in the open source. So that's why I needed to write this code by myself to update it if it's needed. For example, I've started the updating of this code in such a way. For example, let's consider the initial domain with the curvilinear boundary. When you replace the initial domain with a fictitious domain, like a rectangulars, which are like here, by rectangles like here, I can draw the I can triangulate the initial domain. After it, I can update the code such that it will triangulate also the fictitious domain without touching the meshes and the edges of the polygon. It can triangulate the fictitious domain also. This is done to compare the results of the finite differentiating method with the finite element method in the curvilinear, in the initial domain. Okay, it's work which is in this part, one article in the journal which is indexed in the Scopus was published. This is a work which already has been done in this direction. Second direction is the method of fictitious domain. This method is considered for the main part of the equation, as you can see, it's the same as the initial Navier-Stokes equation, but the other component is added to this equation. As you can see on the right side of this equation, there is minus 2 values. One divided to epsilon. Epsilon is given also by user in outside of the original array, but inside of the fictitious array. It equals 1 divided to epsilon. Also, the continuity condition equals the same. There is, for example, in this case, there is an assumption that the boundary area in the curvilinear domain is the same, is equal to the boundary area of the fictitious domain. It's one way of the fictitious domain method. It is a bit easier to solve this kind of the problem with this domain. As you can see, the curvilinear domain is replaced by the domain with a bit simple, which it can be rectangular or parallelogram. Mostly it's a rectangular or parallelogram, and it's a bit easier to solve this problem because of the simplicity of the shape, because of the simplicity of the boundary. There may be some cases when it's not, there may be some cases of fictitious domain method when the minus k multiplied to v is not subtracted. No, it's not on the right side of the equation. Sometimes k might be multiplied to the v, and it may have also two meanings. It may equal to 1, and 1 divided to epsilon inside of the fictitious domain, and the 1 inside of the original domain. In this case, for example, k is multiplied to v, but not subtracted as it's written here. It's also a way of the fictitious domain method. Also, there may be such situation, which I will consider a bit later, when, for example, you have on the boundary of the original domain, you have some boundary condition which is not 0, but the fictitious domain, you consider the fictitious domain as a hard area where there is no flow. You will have the flow in the inside of the original domain, but you don't have the flow outside of the original domain, and there is no flow, but there is a fictitious domain. That's why in the boundary condition of the fictitious domain, it is 0, and the boundary of the original domain, there may be some condition which is not equal to 0. I will consider a bit later this. This equation, this method also had some problem. Dealt with the boundary condition of the pressure. So this method was a bit updated in the article modeling boundary condition for pressure and the total head and in hydrodynamics problems using fictitious domain method, which was written by Smagulov Shaltai Smagulovich, Timirbekov Nurlan Mukhanovich, and Danaev and Nargozov Tursunbayevich. In this method, for the pressure, there are some conditions, some boundary conditions. What is new here? Here is new that the tangent component of the speed at the boundary of the fictitious domain equals to 0. Tangent component of the speed at the boundary of the fictitious domain equals to 0. That's why the pressure at the boundary of the fictitious domain equals to constant. So it's some assumption, some update of the initial fictitious domain method in terms of the adding here some conditions about pressure. What I have, I would like to, what we would like to add to this method to improve the accuracy of this method. For the first time, I consider the Burger's equation. Burger's equation. It's nearly very similar to the Navier-Stokes equation, but it's a one-dimensional equation for the simplicity. As you can see, x changes here from 0 to c, and t changes here from 0 to t. Here, there is some initial condition, g1 for speed, and there is a boundary condition for speed, which is g2, and there is an initial condition of time for time in terms of speed. So this is the Burger's equation, which is considered in the x, which lasts from 0 to x. Now here, using the fictitious domain method, I replace this initial domain with the fictitious domain. Now, as you can see in the first line, x lasts from 0 to 1. So the original domain is replaced by the fictitious domain. Here, equation stays the same. I don't subtract any k or some. I don't multiply k to u, k to speed. I will explain it a bit later. Here, for example, initial condition for the speed stays the same as a J1, and I consider the fictitious domain, which is outside of the original domain, as a hard domain, where is no the flow. So at the boundary of this fictitious domain, I write the condition of the speed as zero. So mu is viscosity coefficient, which can be changed, which it may have some value inside of the original area and another very big value outside of the original area. If why I didn't subtract the k multiplied v, it's another way of introducing the fictitious domain method, that this here in outside of the original area, but inside of the fictitious area, f is already equal to 0, so there is no need to subtract anything here because there is no any flow. So f is 0, but inside of the original area, f has some value. The same with the speed. It's inside of the area there is a speed, but outside of the area there is no speed, there is no flow. As you can see, this equation was solved by using numerical by using approximation. For the exact solution, u equals to t plus sine of p multiplied to x. And also in the second line, some data was given initially in the beginning of the approximation. As you can see in the various, it's considered here the two ratios between the initial area and the fictitious area. For example, the original area, if it lays in the 25% of the fictitious area, the result will be as it's written in the second column of the table. And in the second line, it's considered when the initial original area lies in the 33% of the fictitious area or whole area. The result is as it's written in the second column of the second line. On the second line, the results are written here. As you can see, the results are not so appreciated in terms of the assumptions. Yes, in terms of the assumptions, because fictitious area, the method of the fictitious domain has done very hard assumptions in terms of the boundary of the condition. Sometimes the boundary of the original area may be equal to the boundary of the fictitious area, or sometimes it will have some value, but at the end it will have 0. Like in this problem which I have written here. For example, to have the more accuracy, you need to put the fictitious area more far from the original area. The original area should play in 5% or in 10%, in 10% of the fictitious area, for example, in this case, right? So this is a issue of the accuracy. What we'd like to update here is take into account as you can see in the Burger's equation is a fictitious domain. There is no G2. G2 is not taken into account. Sorry. G2 is not taken into account. For example, this G2, which is the boundary condition of the speed is not taken into account. So we would like to introduce the method using the conjugate equation to improve the accuracy of the fictitious domain by taking into account this J2, the boundary condition of the original domain to increase the accuracy. So how it's done? It's suggested to minimize such this functional. This functional is the integral over time of the difference of the speed, approximated speed, which is calculated using the fictitious domain method, under the real boundary condition of the speed at the boundary of the original area. This difference is integrated over the time, and this is a functional. So this functional have to be minimized in order to take into account the J2. This functional may be minimized using two methods. Results are nearly the same. It's a gradient descent method and the conjugate gradient method. Results are nearly the same. There are maybe there are some just differences between the time which takes to minimize this functional and the iterations which are needed, number of iterations which are needed to minimize this functional. First of all, to minimize this functional, I need to take into account, I can't minimize this functional, just a functional, I need to take into account the condition, this condition of this equation. That's why I subtract from the left part of the equation, I subtract the right part of this equation. So this will be equal to 0. As you can see, I have constructed here the Lagrangian. The second component of the Lagrangian equals to 0. I subtract from the left part, the right part. So the bracket equals to 0. So the functional stays the same. But it's here the condition of the equation is taken into account. So bracket is multiplied to Lagrange multiplier phi, and it's integrated over the time and over the x. So this is a Lagrangian. I will repeat it again. That second component of the Lagrangian will be equal to 0 because the left part of the equation is subtracted from the right part. Okay, now I need to minimize this Lagrangian, for what I need to find the gradient of this Lagrangian. I need to find the gradient of this Lagrangian. So how it's found? To minimize this Lagrangian, I find the increment of this Lagrangian, and I introduce such kind of notations. So as you can see, there is a distortion in terms of G2, which means there will be distortion in terms of the whole set of the speed. So I enter the such kind of notations, which is right in the second part of the slide. So I construct the disturbed problem. Which is right here. For the original area. It's a disturbed problem. There is a distortion in terms of G2. Because when G2 changes, the whole set have to be appreciated to that G2. So that the whole set of the speed have to appreciate to that J2. So that's why the distortion in whole speed will take place. That's why the disturbed problem will be in the form of the third part of this slide. third part of this slide. Okay. Now I construct. Now I construct the problem for the distortion. Now I construct the problem for the distortion. How I construct it? I subtract from this equation, this third part of the equation, I subtract the initial equation. This initial equation I subtracted. So after it, there is a problem of the for the disturbed part of the speed. There is a problem for the disturbed part. Now using this equation, I can find the increment of the Lagrangian. I can find the increment of the Lagrangian. As you can see, it will be like this. It is nearly the same as the first Lagrangian in the form, but there are some changes. It's the increment of the Lagrangian. Here, I need to integrate the second part of this Lagrangian partially. I need to integrate it. So I integrate partially the second part of the Lagrangian by parts. So after that, I will have the conjugate equation as it's written in the second line of this presentation. It will be the conjugate equation. It will be the boundary initial and boundary conditions which are equal to 0, and there is a smoothness, the condition of the smoothness, that the field will be smooth. So as you can see, what is left here, it's an increment of the Lagrangian. Yes, as you can see, after satisfying all the conditions, what will be left here? It will be the increment of the Lagrangian. It's the line which is upper than the last line. This is the increment of the Lagrangian. So the gradient of the Lagrangian will be the expression which is written in the last line. It will be the gradient of the Lagrangian. So it's how the gradient of the Lagrangian is found to minimize this Lagrangian. Now I use the gradient descent method to minimize this Lagrangian, and I minimize it. Also, I use the conjugate gradient method, and also I minimize that Lagrangian. Where, for example, while minimizing this Lagrangian, uct is the independent variable. So by changing, by using the gradient, by doing some iterations, I find the appreciate uct to minimize this Lagrangian. In the so gradient descent method is written in the first line. In the conjugate gradient method, it's a bit different from the gradient descent method. Here the gradient is taken to the more appreciate gradient is taken using such formulas to do the number of iterations less, and to do the time taking to minimize this Lagrangian less. The conjugate gradient in the conjugate gradient method, such kind of finding the gradient is used. There are two methods of minimizing the Lagrangian, which was considered in my research. So as you can see, there is results. There is a results for the exact solution, the same t plus sine of p multiplied 2x. In the first column, there is a functional, the minimized functional, which is minimized by gradient using gradient descent method, and which is minimized by conjugate gradient method. As you can see, the minimized functional is very low. A number of iterations in the conjugate gradient method there is 97 iterations, and in the gradient descent method there is 97 iterations, and the conjugate gradient method there are 27 iterations, which is smaller than the 97. And there is a difference. Also, time spent in seconds of two methods. This is the result for another Xi, which lies in 33%. Here, the Xi lies in 25% of the fictitious domain. Here the original realized is 33% of the fictitious domain. So this is the results. So functional is minimized and difference is right in the third column, in the fourth column. Okay, so this is a work which has been done in the one-dimensional equation. Now in the two-dimensional is still in process. We have tried to minimize. There is a work on the formulating the conjugate problem of the two-dimensional Navier-Stokes problem. Firstly, we have constructed the conjugate equation of the Navier-Stokes equation, two-dimensional Navier-Stokes equation, by minimizing the functional. But the conjugate equation was a bit complex, and in terms of finding gradient, there are some difficulties, but still this work is in process. Here in this presentation is presented the way of finding the conjugate equation for stationary problem, but not by minimizing the functional, but using the Lagrangian principle. Please consider such kind of a stationary problem. In the second part of this presentation, it's written more expanded. These operators are introduced. This A1 and A2 is introduced. It is the same as it's written here. The equation is the same as written here. And the supposed two conjugate supposed conjugate operators are introduced, A1 star and A2 star. Also introduce variables like U star, V star, and the Q. A1 star is in the format is written in the second part of this equation, or in the second part of this presentation. A2 star also written in the second part of this equation. So okay, now here what I have what is done is that the first equation, A1, not A1 star, but A1 is multiplied to U star and the A star, and all two equations are summed up. And there is a process of integrating by parts the expression which is written in the first part of this, in the above of this presentation. So it's integrating by parts. So taking into account the boundary conditions of the speed, the first part of the result of this integrating will be equal to 0, but second two integrals will stay as they are. So it's the same integration for the pressure part. So first to be the first part of this pressure result of the integrating to be the first integral to be equal to 0. Such kind of boundary conditions are introduced. So as you have only second part, two integrals, two components. So using this integral, taking into account the velocity continuity condition, this integral also will be equal to 0. Similar equation is integration is written. Some integration written in the middle of this presentation. So in the operator form, if to add these equations, so I have written here V1, V2, there should be U and the V, and the U star and the V star. There is a bit some mistake in the last line of this equation, last line of this presentation. You can, in the operator way, you can write in such a way, which means that the Lagrangian principle is satisfied. Therefore, the conjugate problem of the two-dimensional stationary problem, which was considered above, is like this. This is considered as a conjugate problem of the initial problem, of the initial stationary problem. In this direction, the work is still in process. So it's planned to consider further. It's planned for the consideration of the constructing of the equation for two-dimensional equation, and to minimize, to take into account the boundary in the original area domain method. So that's all the